So this is Mohammed. I'm a Master's of Stats student.
And I'm Delaney. I'm a Master's of Applied Mathematics student. And today we're going to be presenting to you a paper titled Influenza Forecasting Framework based on Gaussian processes. So we're going to begin this presentation by providing a brief introduction, which will motivate and state the purpose of this work. Following this, we're going to present the outline of the model framework, the results that were achieved using this model, a brief conclusion, followed by our own critique of the work that's presented. So last year alone, the seasonal influenza epidemic was responsible for 38 million flu cases, 400,000 hospitalizations, and 22,000 deaths. And given the magnitude of this effect, reliable forecasts of future influenza development are really crucial to help improve public health policy and allow for better resource allocation and development. So given this information, the Center for Disease Control and Prevention has decided to not only regularly publish influenza-like illness or ILI data, with only a publishing delay of approximately 1 to 3 weeks, but they've also invested into this field by launching a challenge for research groups to forecast influenza activities.
So this brought to attention the field of forecasting. So here is some state-of-the-art models. We have the MSS, which is multiple shooting for stochastic systems. This is a physical model, ODE-based, and it takes into account factors like humidity, say. It has its advantages and performs well, but not so popular for seasonal modeling like our case. Of course, time series models are found helpful here, particularly SARIMA, which is seasonal autoregressive integrated moving average model. You can now learn about this in Stats 929 or 443 if you are an undergrad. In essence, autoregressive models are linear regression models which consider past data. So mentioning linear regression, we also have LinEns, which is linear ensemble, which takes average over the best 3 performing linear regression models. LinEns is actually close to our new work.
So it can be shown that this linear ensemble model actually outperforms the other models that we mentioned on the publicly available influenza-like illness data set. However, this linear ensemble model assumes a deterministic relationship between the epidemic week and its case count, and that doesn't reflect the stochastic nature of this trend. And so having said this, it begs the question, would a similar framework to this linear ensemble model, which now assumes a stochastic relationship between these variables instead, would that provide a better performance? And this is really the motivation for this work. Where the goal of the paper is to develop a new framework for seasonal epidemic forecasting that's based on Gaussian process regression, and then to compare the performance of this new framework to the aforementioned state-of-the-art models and see which performs the best.
So here is the framework data setup. Fortunately, in this work, we have a setup similar to what we have seen in class. More precisely, our training data X is set up in a D by N matrix where rows are features and columns are data points. The only difference is that we have noisy data and the trend f of x is of stochastic nature. We let x star denote a single test data point. As usual, our predicted value will be y hat, which is f hat of x star, where f hat is the model we design. Instead of assuming a deterministic form of f, and so of y and y hat, like we do in linear regression, for example, Gaussian process regression assumes that f is of stochastic nature. To clarify this more, imagine that for every x, f of x is a random variable. As seen in class, when the prior distribution is assumed, the same is done here, but our prior follows this form. The covariance matrix you see depends on something called the kernel function. And for the work here, this kernel is Gaussian in the, like you see written below.
All right, so it's important to note here that different from what we've seen in class is that we're now working with a distribution of functions. And this becomes really obvious when you look at the left of this figure at the prior distribution, and you see that there's a clear distribution of gray curves or functions that have a mean at 0, which is highlighted by this bold gray curve. And in order to get from this joint prior distribution of functions to a posterior distribution that we can use for forecasting, what we do is we only take the subset of these functions that pass through our observed data points. And you can see this behavior on the left side of this image, where all of the chosen functions in the posterior distribution are passing through these black markers, which are supposed to represent the data in this case. And to be more precise, this posterior distribution is given by, has this form where the mean and the variance depend on our test data point. So yeah, this is the setup that we're working with.
So now that we know how GP regression works, we can look at the data we want to perform on. Starting with some notation, the Dij denotes the number of epidemic cases recorded in week J of season I. The season will basically be like the year number, and J is some week in the season. So say some week around the end of the year, winter time, when people may experience flu symptoms. The J star and I star will denote the current week and current season. The influenza-like infection data set is basically the DIJs, which are the counts of the cases for all previous weeks and seasons up to the current season. And that data takes time to appear, so usually 1 to 3 weeks publishing delay. The goal here is to forecast the count at a certain target week ahead. So if we have that y hat indexed by t is di star j star plus t. And for example, when t is 1, we mean next week.
So having described this data, we now want to look at how to formulate our algorithm. So the first step is to choose a subset J of the possible weeks that we want to work with, that we want to include in the training set. And in this paper, they've actually shown a theoretical result where the convergence of the predictive variance is slower for larger J. So the more weeks that you consider, the slower convergence that you have. And for this reason, the authors decided to restrict the possible subsets to the previous 4 weeks only. So the first step is really to pick one of these subsets. Then on this subset, the first step is to assemble the corresponding training set. So our design matrix xj is going to contain the number of cases in week J of season I, and then the corresponding observations is going to be given by the number of cases that were observed in the target week that we want in the previous season I. Once we have our training set, we're able to train this Gaussian process, and using what we have before about what Gaussian process regression is, we can use a posterior distribution to calculate the distribution of y hat at our particular target week and on our particular set of weeks. Now with this, we can set this y hat value to be the mean of the distribution that we're going to calculate, and we can do so because it depends on all known information. Now, having said this, and because we have this for this specific J, we now want to repeat all of these steps for all possible sets J in this previous 4-week subset. Once this is done, we want to determine the best 3 performing sets, and we're going to do this using 2 different validation sets, the 2010/11 and the 2011/12 seasons. And once we've determined these best 3 performing sets, we can then compute our ensemble forecast, which just means that we're going to average the best 3 performing probability densities. And so we get a final predicted value y hat for our target time, capital T, which is given just by the average of the predicted values for these 3 best distributions.
So as the figure explains, our forecast, which is a blue line, is reliable because the true data points, the red X's, remain within the 95 prediction or confidence interval, which is the purple region, 95% of the time. This works for different forecasting targets ahead, like 1 week or 3 weeks. To get those figures, note that we needed 30 predicted points for each, and each has its own model. So we needed to train 30 times 2, which is 60 models. In order to estimate the accuracy of the framework, it makes sense to use retrospective forecasting, which means that a previous season is treated as a current season, so we can compare the forecast with a known true outcome. And the accuracy score suggested by the CDC is something called log score, which is a logarithm of the probability of the forecast being within an interval around the true value. The reason to choose a probabilistic criterion here is that probabilistic forecasts allow for an accurate uncertainty, like for an accurate uncertainty estimation. And this is of much more relevance for disease forecasting than point forecast. So conclusion, the main contribution is a new GP-based framework which outperforms 3 state-of-the-art models. Actually, it performs better than a 4th one, which is called the EpiDeep, but which is deep network based, obviously. But we didn't mention it because the comparison criteria is mean square error, and it isn't what CDC criterion or what CDC uses. Anyway, this work is obviously significant, especially if COVID becomes seasonal. This model may help the CDC be more prepared.
So having said all of this, we'll do a little critique of what we thought. So the first thing that we're going to talk about here is the advantages. And the first main one is that it's incredibly computationally efficient. It can be run on any personal computer in minutes, and you can run you can train hundreds of Gaussian processes in this time, which is really important because we know that we have to train an individual Gaussian process for each test point. And for each season, we can have 30 or up to 52 different test points, and we could have multiple different targets. Now, speaking of the targets, the models are actually easily extendable to very interesting targets. Now, in this work, they really only looked at 1, 2, 3, and 4 weeks into the future, but you can actually get some really powerful information out of this model. This comes in 3 different ways. The first one is that you can predict the peak incidence, which is the maximum number of cases in a given week. Here we're assuming that a season lasts 52 weeks, so the season is the entire year. You can also predict the timing of the peak incidence by looking at the argmax. And finally, you can predict the final epidemic size, which just means the total number of cases that season by looking at the sum of the total of the cases over all of the weeks. Now, finally, this model is applicable to any data set, including real-time data. The only data that they worked on in this paper was the official CDC data set because it allowed for easy comparison. But in real life and in real life forecasting environments, you can use real-time data available, such as Google flu trends, Twitter texts, and visits to Wikipedia pages, where you're essentially just looking at searches for common flu symptoms, such as cough, fever, etc. And this can be really useful if you want to predict in real time, given that the CDC's data set has that 1 to 3 week delay that we've mentioned. Now, finally, to finish off here, there are some disadvantages. The first one being that the model presented isn't a physical model, which means that it can't provide insights to key parameters that could be describing the disease spread. For example, something like the MSS model that we mentioned, which is an ODE model, is physical, so it would be able to do this. And finally, as well, it's not really applicable for non-seasonal epidemics, unfortunately, because it requires that training data be available. And with that being said, thank you for listening, and we hope that you have a nice day.
Thank you.